My name is Pax Haymeyer. I'm the Associate Director of Graduate Programs at the Stanford Center for Professional Development, and I'm here with Marco Pavone, Jeanette Bogue, and Dorsa Sadiq, who will be leading a 2-course sequence in robotic autonomy that they just recently redesigned and redeveloped. And so we're here to find out about their research, robotics, and their course. Great. We'll start off with just each of you introducing yourselves. So Marco, could you introduce yourself touching on your research?
Sure. I'm a faculty in the Department of Aeronautics and Astronautics, where I direct the Autonomous Systems Laboratory, and I'm co-director for the Center for Automotive Research at Stanford, and I'm also affiliated with the Human-Centered AI Institute. My work is on decision-making and AI algorithms for robot autonomy, with application to self-driving cars and autonomous aerospace vehicles.
Perfect. Jeanette?
Thank you. So my name is Jeanette Bogue. I'm assistant professor at the Computer Science Department for Robotics, and I'm directing the Interactive Perception and Robot Learning Lab in the CS department. I'm also affiliated with the Human-Centered AI Institute, as all three of us. And my research is at the intersection of robotics, machine learning, and computer vision, and all the algorithms I've been developing in the course of my years of research are applied to the problem of vision-based or sensor-based robotic manipulation and grasping.
Thank you.
Right.
Dorsa?
Sure. So I'm Dorsa Sadiq. I'm an assistant professor in the Computer Science and Electrical Engineering department here at Stanford. I'm also the co-director of the AI Safety Center, and I'm also affiliated with High Human-Centered AI. So my research is at the intersection of robotics and human-robot interaction, thinking about design of algorithms for autonomous systems that safely and reliably can interact with people.
Perfect. And Dorsa, as a follow-up, I know you have sort of an interesting path to the research that you're currently doing. Can you tell us a little bit about that?
Sure, of course. So at the beginning of my PhD, when I started thinking about what to do, I was looking at robotics and formal methods. So I really wanted to work at the intersection of these two fields, where formal methods is this field where you're looking at giving correctness guarantees for autonomous systems. And the goal of my PhD thesis was to give guarantees for autonomous cars. The autonomous cars were becoming a thing at that time, and I really wanted to be able to give provably correct guarantees for these systems. And soon I realized one of the biggest problems with autonomous cars when you're trying to give guarantees about them is just dealing with humans. There are all these human-driven cars around us. And if we don't have good models of them, or if we have made-up models of them, then we can give some sort of guarantees. But it's important what sort of models we are picking and how we are deciding, like, what are the humans around us are doing. So I do think this area of human-robot interaction is really interesting, and that's how I got into it and how I started thinking about interaction and the fact that autonomous systems, robots, are coming into our everyday lives, and we need to think about that interaction and the fact that there are humans around us, and we should model them in a way that's useful for our autonomous systems and robots.
Fantastic. So you touched on there one of the big challenges for roboticists today. What are some of the other challenges for roboticists?
Yeah, so I think it's a very good time for robotics. I think there are a lot of interesting opportunities and interesting challenges in robotics. So one of the biggest ones is, I think, dealing with humans and dealing with uncertain environments. I think in addition to that, we have a few other challenges, things like generalizability and how we can think about like combining model-based and data-driven techniques and how we should go about that for solving really difficult robotics problems. And then going back to uncertainty, I think another difficult problem is thinking about giving guarantees and safety and how we can plan like under uncertainty and how we can give probably correct guarantees and going back to the safety problem, how can we give guarantees for our autonomous systems?
Marco, I know you also work a lot on decision-making in uncertain environments. Can you elaborate on that challenge?
Yes, absolutely. Robot autonomy really entails designing robotic systems that need to operate in situations that cannot be foreseen at the design stage. And those situations require reasoning. So the challenge is how do we provide assurances and guarantees for robots that need to respond to situations that cannot be foreseen at the design stage. So a good portion of my work is devoted to techniques that allow robots to generalize their behaviors to situations that cannot be anticipated at the design stage, and in a way so that we can have trust in and confidence in what the robot does.
And Jeanette, your work works you also focus both on this problem of generalizability as well as some of the challenges that Dorsa touched on the models that we use. Could you develop that?
Right, yeah. So maybe also just to expand on what Marco just said, the problem of having a robot act in an uncertain environment is also something that I'm very interested in. It's a very hard problem, and it's typically engineered away in environments like car manufacturing factories, for example, where the environment is designed in such a way that a robot doesn't have to deal with uncertainty at all and can just execute pre-programmed motions. But if we aim for having a robot actually help us in our house, at home with annoying tasks that nobody wants to do, or in dangerous environments that we don't want people to actually be in, a robot will experience all these unstructured environments. And it only has sensors that basically give it access to partial information only. And still, it needs to be able to make safe decisions on how to act in this environment, and also robust ones. And even if it makes a failure, it should be able to recover from this failure and redo. And these are all challenges that we don't know really how to do today, and it's very exciting to work on those. Yeah.
So sort of building on what you said, or if Marco or Dorsa, if you want to chime in, but you've talked about in the past also the challenges of collecting data, that it's very expensive and can be dangerous to collect data with robots. Can you build on that, or if anybody wants to speak to that?
Right, so I can maybe start talking about this. So there is a huge opportunity right now in robotics to actually use a machine learning-based method to enable robots to do tasks that were previously not possible, because maybe we cannot have good models, like for example in the human case, or also in terms of physics-based models of, for example, fluids or deformable objects. And learning-based methods allow us to maybe learn models instead of having to hand design those for these difficult physical processes, for example. But current machine learning approaches rely heavily on large amounts of data. And in other applications like computer vision or natural language processing, this kind of data is relatively easy to collect and to label. But in robotics, what it means to collect data is typically to have an actual physical machine interact with the environment in such a way that it doesn't destroy itself or is a danger to anyone around it, or breaks anything in the environment. And also it takes just longer for a robot to execute a motion rather than just looking at a picture and labeling it. And therefore, it's actually much bigger effort for a robot to collect that kind of data that is required for current machine learning techniques. So I think there's a huge opportunity in robotics to use machine learning, but it also poses a challenge to actually, that is very specific to robotics, where it's hard to collect enough data for current algorithms.
And I think just to add on what Jeanette was talking about, I think another opportunity here is, like, we've seen all these advances of deep learning in natural language processing and vision, and one of the reasons is data. But another interesting thing is we've been using model-based approaches for robotics for many years, and these model-based techniques can provide really good priors, really good inductive biases, and actually help us improve a lot of deep learning type techniques that we have. So it actually helps us improve machine learning too, having this new problem that we have, in addition to having extra data. I think there's a lot of interesting directions that one can take, thinking about data-driven and model-based, and how we should combine them to solve some of these really difficult problems in robotics.
Yeah, and if you think about it, it's interesting how in the AI community, oftentimes people consider the abundance of data as a challenge. In robotics, we have a completely different challenge. It's the scarcity of data, which, as Dorsa and Jeanette were saying, opens up an opportunity in order to devise techniques that are really tailored to robotics, and creatively combine model-based approaches with model-free approaches, and carefully designed ways of collecting data, and so on and so forth.
Fantastic. What are some of the other opportunities that you see for roboticists today, Marco?
In terms of research or in terms of applications?
Both, yeah.
In terms of research, so we talked about generalizability, we talked about how to interact with humans in a seamless way. I would like to reiterate the challenge that an opportunity that Jeanette mentioned, which is the one of interacting with the environment. Usually for robotic systems, as long as they do not touch something, you can still do it. But the moment they start touching, manipulating, and affecting the environment, then it becomes really a gray area with a lot of open questions. And then the aspect of safety. Safety is a difficult concept in the context of robotics. First of all, different applications demand different levels of safety. Of course, safety for self-driving cars is different than safety for a warehouse robot. And second of all, it's a concept that needs to be traded off with efficiency, meaning that as humans, we constantly make good judgment calls in how to properly trade the safety with efficiency. It's relatively easy for a self-driving car to be safe, it just doesn't move. Or it's relatively easy for a self-driving car to be very efficient. It always go at maximum speed, but sometimes it might collide. The question is, how do you trade the two in such a way that you find the sweet spot? Now, finding techniques to achieve that trade is still very much an open challenge.
Dorsa, could you build on that? Because I know you've done research both on that sort of trade-off of efficiency and safety, as well as the interaction with humans, right? Because robots can start influencing humans as well.
Yeah, so I think the influencing humans is also another interesting aspect of it. And it goes back to like interacting with the environment too, right? Once we are touching the environment, we are changing the environment. Once we are interacting with the person, we are changing the person, we are influencing the person. And thinking about how our actions as an autonomous car or as a robot is going to influence humans and how are humans going to respond and how their models change is actually really interesting and challenging. And just to build up on what Marco was just talking about, so we have all these different challenges which are really interesting, and we're doing research on them, and it's exciting because we're teaching a class that's trying to like cover all these topics that are these new exciting topics in robotics. But I think there are a lot of interesting opportunities in industry too. So I think these are like academic, like from an academic perspective, these are challenges and problems that we can go about solving and learning about. But from an industry perspective, we've seen robotic systems like in factory floors, like mainly working in factory floors and doing awesome things. But we haven't really seen them like coming into our everyday lives yet, right? Like autonomous cars is kind of a step in that direction. But in general, I think there's a lot of interesting opportunities from an industrial perspective, from an application perspective, thinking about robots coming into our everyday like life. Thinking about helper robots or companion robots or robots helping in like hospitals or in homes, like especially with our like elderly population increasing, I think it's an interesting opportunity to look at. There are other applications like agriculture or like space, like as Marco works on, that we can think about how robots can help us and actually coming into our everyday lives in a more like tangible way.
Yeah, and that's a very good point. And in fact, one of the key motivations for us to develop this course series is to, in a way, democratize the tools behind robot autonomy in hope that we can spur a new set of ideas from industry, new set of applications that, as of now, we are not even aware of.
I think that might be a good transition. I want to come back to some of the things we've talked about, but maybe to discuss the classes themselves. So Jeanette, what is one of the things that you're most excited to teach in this course?
Right. So as Dorsa already said, we are actually touching on 4 areas within the course, which is learning-based method for robotics, systems integration and verification and validation. We're looking at physical interaction for manipulation and grasping of mobile robots, and we're looking at interaction with humans. And none of these topics is really taught yet, at least at Stanford, in this integrated way on an actual platform. And so first of all, I'm excited about this kind of cut through all of these areas, because typically in robotics, people are very focused and almost a bit siloed in their particular areas. So they are perception experts, control experts, motion planning experts, human-robot interaction expert, and they typically don't know the field of these other fields very well. But a robot is actual a physical system in which all of these things have to come together. And if you put modules together that are developed in an isolated manner, they may not actually work that well together if you put them into a system just as is. So this course actually provides this opportunity to put all of these different kind of components of a system together and actually see what happens and what is required on a systems level as well. So that's something I'm very excited about, actually.
Yeah, so the idea is that, of course, people will become experts in a particular domain, of course, decision-making or perception or manipulation and so on. But by taking this course series, they will also develop enough breadth of expertise so that they will be able to reason in a principled way about the interfaces between what they do and the other capabilities in the autonomy stack, so that they can place proper assumptions, they can consider interactions among the different modules of the autonomy stack that have the potential to really work in practice.
So, Marco, this originally was just a 1-quarter sequence that you taught, and now it's expanded in 2 quarters, and you're working all 3 of you together.
Yes.
Can you explain, so I think you've already touched on it, but what was the impetus behind expanding it into a larger course and bringing in additional instructors?
Well, the impetus behind was very much aligned with what Jeanette said. That as part of my education, I realized that I had a pretty good grasp about techniques in decision-making and controls, but I did not have enough exposure, in my opinion, to other fields of robotics. So one of the main motivations behind designing this class was to give students the opportunity to have exposure to the different modules of the autonomy stack and how they integrate and how they talk to each other. So I started teaching this class 3 years ago with the goal of teaching the foundations of robot autonomy, so the most basic capabilities to make a robot really autonomous, capabilities such as trajectory optimization, decision-making, vision-based perception, localization, and mapping, both the mathematics behind the algorithms, how to code these algorithms in the robot operating system, and how to deploy the autonomy stack that the students incrementally build throughout the course on a physical machine, really in an effort to teach students how to think at the system level. And the response from the students has been enthusiastic, which prompted me, together with Dorsa and Jeanette, to think about an advanced version of this class where we go beyond the basic capabilities and actually we teach state-of-the-art capabilities that in the end are really the ones that are opening up all the new exciting applications that were discussed before. The new exciting capabilities, as already mentioned, include learning-based methods, in particular with the perspective of allowing a robot to generalize to new scenarios that have not been seen prior to that experience, verification and validation in order to teach students how to reason about safety for a system that has reasoning capabilities, and then interaction with the environment, interaction with humans. We believe that through these 2 classes series, the students will be equipped with a set of tools that will allow them to really think about new research challenges on the one hand, but also new application opportunities on the other hand.
Dorsa, so building on Marco's last comment, what would you hope that students take away from this class, the 2-course sequence or the second course?
Yeah, so I think one interesting thing that we get out of this robotics series course, and I think I really want the students to get out of it, is to kind of understand that if you want to build a really full like robotic system, you should not be scared of like touching the physical robot. You should actually code. So understanding that you need all these different fields to come together to solve a really challenging robotics problem. And I think like a lot of these boundaries that we put in between departments are very superficial boundaries, right? Like robotics is kind of like a true interdisciplinary field, and this class is also cross-listed between computer science, aeroastro, electrical engineering. So I think it's very substantial. It's very, actually, I don't know what to say here. So I think it's very useful for the students to kind of be able to use a physical system and code it up and actually like deal with real sensors and understand what are the real challenges that you would have in a robotics system.
Yeah, maybe I can build up on top of this as well, of what you said. So the thing that I really love about robotics is that it is interdisciplinary. So you can come in with almost any kind of knowledge, any kind of background knowledge you have, and contribute to the field. It's something I really love about it. And I hope that in this course this is reflected by actually touching upon all these different areas.
So do you hope it also appeals to a broad range of students, that you're not
Yes.
just pulling in aero and astronautics or just CS, you're hoping?
Right.
Not only that, but I think that that will be instrumental to the success of this class. For example, for the deployment of the software on the physical platform, we divide students in groups, and we make an effort to make sure that within each group there are people with a different background, really to reflect this idea of a need for system thinking, interdisciplinary thinking when it comes to robot autonomy.
So robotics is a team sport.
Yep.
Yeah, definitely.
What do you think will be, Jeanette, what do you think will be the most surprising thing that students will take away from the course?
Maybe how hard it is. Because it's, like if you have never worked with a robot before, the things you are consciously aware of are movies, like Hollywood movies, or also YouTube videos from awesome companies like, for example, Boston Dynamics, right, where they show these capabilities. Or you see research results that are, of course, somewhat biased towards the positive outcomes. But everyone who has worked with a real robot knows that for making a robot work once, there have been weeks and weeks of development and failure behind it. And I think that is something that you can take away if you get to work with a real physical robot platform.
So they may,
Yeah, and I completely agree with what Jeanette just said, to the point that actually in the class we put a lot of emphasis on teaching also software engineering principles, specifically for robotics. On the one hand, to teach students how to, if possible, minimize the effort, but at the same time, how to be able to isolate failures and quickly address those in an effort to incrementally improve the performance of the robot.
So they won't leave the class with a fully functioning walking dog that moves around. It'll be a little bit less ambitious.
I wish, yeah.
Maybe coming back to the research, Jeanette, you've talked about this problem of generalizability, and you work on integrating multiple sensors in a robot. Can you maybe elaborate
Sure.
on that?
Yeah, I wanted to mention this already when we talked about opportunities, because something that is very special for a robot as compared to maybe methods in computer vision or natural language processing is that a robot is a physical system that has many sensors. So it doesn't just have a camera or only a microphone. It also has skin. It has sensing in all the joints, so that the robot actually knows where all its limbs are. And it makes physical contact with the environment that in turn change the sensory input to all of these sensors, right? So if it physically interacts, there might be a sound, or there might be motion in the camera, or there might be feedback on the tactile sensors. And there is an opportunity here to exploit all of these different sensors that are concurrently excited in a way. But at the same time, it's a challenge to actually integrate all of these different sensors, because they have a very different structure and dimensionality and frame rate and all these things. And it's not clear how to really do that well, but it's one of the core questions that I'm asking in my research together with my students.
So this is both an opportunity and a challenge.
Yes, exactly. Yeah. It makes things easier because there's more information, richer information. At the same time, algorithmically, it's harder because it's unclear how to fuse this information, how to really exploit it. Yeah.
Yeah, and I guess the same thing kind of happens when you're dealing with humans, right? When you have humans interacting with robots, there's this new setting where you have interesting interactions going on between very complex agents that are decision makers or thinking about what they're doing. And it's interesting to be able to like extract kind of lower dimensional embeddings of what is this interaction that's happening between the humans or between the robots, and leverage these lower dimensional representations, let's say like intent or goal, and use that for the robot to plan better, to plan, to positively influence humans or to work better and collaborate with humans.
Great. So you're going to be teaching, the next crop of roboticists. So Dorsa, what do you think? Your research on human interaction with robots. What do you think the next 50 years will hold for that?
Yeah. So it's an exciting area, and I hope that in the next 15 to 20 years, we would be able to have robots seamlessly and easily collaborate with people. I really want a robot to come and try to do a task cook a meal with a person. I would really want to see that in the next 20 years, having a robot in our homes, in our kitchen, being able to figure out, when I start chopping the onions, know what is the next thing to do and just come in and help me in real time. And there are a lot of real robotics challenges there too. It's not just the human interaction, just real-time planning for robots is really hard. But there are also these challenges of figuring out what the intent of the person is, predicting what the person is doing, and easily come into people's spaces and collaborate with them, either through touch or just through motion and interaction with a person. So ideally, I would want to have robots in homes helping people.
So Jeanette, building on that, I know you've talked about one of the challenges of, for instance, a robot working in the kitchen which I didn't know, it's hard to model how to grab a soft food or how to deal with rubble. Can you build on that as maybe where you see the kind of research you're doing going in the next 50 years?
So it's very hard to predict what's going to happen in the next 50 years. But the example that Dorsa just made is actually a very interesting one for me as well. My core expertise is not in human-robot interaction, but my core expertise is in the perception capabilities using all these different sensors, for example, which clearly are required to also make that scenario work. So it's a nice scenario to actually think about also these core challenges I'm looking at. So it's also a very exciting scenario for me. I also think that robots are definitely, right now they're really bad at anything except from you put them in a car factory, right, where everything is nicely controlled. But they're really not very good unless you control the environment and you let them do a very specific task. So I'm really hoping that at some point they can do these kinds of tasks, and I think it will be much easier to have a setup where you have some kind of shared autonomy or a collaborative system because it's much harder to aim for full autonomy. I think this human-robot interaction really gives an opportunity to speed up this development because, a robot could actually help a person to ask a question or ask it to actually show it how to do something by guiding it, right?
Yeah, there is a say robotics whereby what is difficult for a human can be very easy for a robot, and what is easy for a human is extremely difficult for a robot. Robots are extremely good at extremely precisely positioning something with millimeter accuracy. But when you ask a robot to cut an onion, then it becomes an open problem. So one of my hopes is that in the next 20 years, we're going to change a little bit this say in robotics in order to allow a new generation of robots that can really work, for example, alongside humans in order to relieve some of the most dangerous or annoying tasks. In addition, given also my aerospace background, currently there is a lot of hope and that robot autonomy will allow to accomplish tasks in space, either in orbit or on other planets or planetary bodies that currently cannot be accomplished through teleoperation. The big challenge, though, is that because of all the reasons that Jeanette mentioned, in particular that robots are bad the moment they have to operate in an open environment, there is very little trust about these technologies, to the point that people prefer not to consider missions because there is an unacceptable level of risk that the robot might fail. Well, I hope, again, that in the next 20 years, this will change, and this will open up new opportunities to accomplish missions in orbit. For example, repairing a satellite with a satellite mechanic or something, and also explore new environments. For example, right now we know that there are a number of planetary bodies with an ocean within. So I think it would be a dream for myself and for the robotic community to be able to go to those places and visit those oceans and possibly look for forms of life.
Anything you want to add to kind of the future, the next 50 years maybe was too ambitious, but the next 5 to 10 years, what you see on the horizon for robotics? Jeanette?
Yeah, even in 5 to 10 years, it's relatively hard to predict. So, I mean, there's this big question about autonomous driving, right? And if we will see autonomous cars in the near future. I'm very skeptical about this within actually the next 5-10 years, but maybe you can, I don't know what your opinion actually is, but even if you don't want to go for full autonomy, even having a shared autonomy system with a person who maybe has to take over is very challenging to do that. So I don't even quite know in that field how it's going to go. In terms of manipulation, which is kind of what I'm mainly working on, I think there are probably more interesting useful solutions when it comes to warehouse robotics. This seems more in reach when robots have to actually deal with an absolutely huge amount of different objects that come in every day to warehouse and have to be packaged. So I think we made really good progress in the last 10 years in that, and research on just pick and place tasks in these environments has moved now more and more to industry as well. So I think this could be something to consider in the next 5 to 10 years, that it's actually going to happen, that this is more and more automated. And
robotics goes in waves, and there are years where there are very high expectations, and then we go into a winter of robotics and so on. I usually joke by saying that in the 1560s, people were considering general AI robots that could do everything in our houses and so on. 50 years later, the robotics community has delivered a Roomba, which is a great robot, but it's very far from an assistive robot that can do anything. But I think that there is a difference with respect to the different waves. First of all, now we have massive investments in this field. Second of all, I think we have brand new tools that allow us to tackle problems that previously were very difficult to be tackled. And three, there are a number of focused applications like warehouse robotics or drones for agriculture and so on, which are maybe a little bit less ambitious than, say, general AI for a robot assistant, but still extremely useful from a societal standpoint and much more achievable from a technological standpoint. So I would say it's difficult to predict what will happen in the next 10 to 20 years, but at the very least, I would say that this excitement about robotics will stay. And I don't see a winter of robotics.
We're still in the summer of robotics.
Yes.
So just to add on that, so I do agree that like if you look at AI, like at the beginning, you really wanted to build this intelligence that's going to solve like everything and is going to be close to like humans' intelligence and everything is going to be great. And that was just too much of a like big goal that was impossible. And then we saw the winter of AI. And then later, I think what happened was there was a shift of like paradigms, right? Like people people started thinking about, okay, I don't really want to have this intelligence, this super intelligence that works as well as humans. I just want to build a system that's useful, that can like do this thing that I really wanted to do, like drive or do this thing in like warehouse settings. And I think the same thing is about robotics. As long as we build systems that are going to like help people and be useful, I think that's pretty good. The other point that I wanted to make about driving is, the technology for driving, I think we've made a lot of advances there, and it's very close to like being there, right? But there are a lot of other factors that come in when you think about deploying these systems to like our real like roads. And I think those are also other challenges that one might want to think about, like legal challenges or again, safety challenges, like how do you insure the cars? What happens in the case of accidents? So I think those are also some of the challenges that are really real when you think about deploying a robotic system into the real world. Yeah.
Just building on that, can you talk maybe, doesn't have to be predictive next 5 to 10 years, but how will robots change the way we act? So if robots come into the kitchen or on the roads, how will that change the way humans act?
Yeah, so I have a story from myself. So I used to live in San Francisco until like a month ago, and there you see all these autonomous cars testing in really difficult like situations because the city is quite challenging. And what happens is a lot of times these cars get stuck at intersections. So I see them getting stuck at intersections a lot. And what happens now is when I see them, I just go around them. And it's kind of crazy that based on that like 3 interactions that I've had with an autonomous car, I've decided to change my behavior and go around it. So it is interesting to look into how like humans adapt to these autonomous systems that we are putting in. And some of it is not predictable. It's actually really hard to predict what happens if I put in like 10 autonomous cars on the road. How is that going to affect traffic? Like how is that going to affect some of the larger objectives and global objectives that we care about as a society? So I think that's an interesting active area of research, and it's hard to predict right now, like what happens if I put in a helper robot in homes, and what is the long-term effect of that. The short-term effects, we are doing some works on that, so thinking about the short-term like interactions and how that is going to affect people, but repeated long-term interaction and effects of that is really interesting to study.
And we're back, and we have a new guest. So can you introduce this robot?
You want to introduce it?
Sure. This is the platform that we use throughout this course series. And this platform has a set of representative sensors that you may find, for example, on a self-driving car, for example, a LiDAR sensor, a camera, fairly very capable processors, and also a gripper in order to test the algorithms that we will be covering in this class about manipulation and how a robot should interact with the environment. Now, as part of the class, we also provide a simulator whereby before deploying the autonomy stack on the platform, we actually run tests on a simulator that quite closely emulates the capability of the robot. Unfortunately, for the first year of this class, the platform won't be available to remote students, but those of you that are local will be welcome to come to our teaching lab and actually work with the physical platform itself.
Can you talk, so what are the kinds of tasks that you will be asking the robots to perform, or people to make the robots perform?
Right. So maybe in the first course, so Robot Autonomy 1, the main task of the robot will be navigation, basically in a maze, right? Like in a kind of fake city, essentially, and we'll heavily rely on this really interesting sensor that actually, if you're studying computer science or any of the other engineering degrees, you seldomly, I think, have the opportunity to actually work with that kind of data. I myself have actually never worked with that kind of sensor, so I'm also excited about that. And then, so that will be about navigation. And then in the second edition of the course, so Robot Autonomy 2, we will also, amongst others, look at grasping manipulation capabilities, where we basically want the students to be able to pick up particular specific objects and maybe bring them to specific places. So combining manipulation capabilities with navigation capabilities. And of course, they will need to use visual sensing to actually find these kinds of objects and maybe react appropriately when the object slips out of the gripper and things like that. So that would be very interesting.
So all of a sudden, this fairly simple task become a task of perceiving the environment, localizing the robot within the environment, reasoning about the environment, classifying objects for what they really are, and then scheduling a series of tasks to accomplish a goal. So this is to say how robotics is a challenging field, because even easy things like moving objects around entail a number of fairly complex capabilities that we as humans take for granted, but that actually require a lot of mathematical understanding of the problem and a lot of software engineering skills in order to realize that mathematical understanding into something that actually works.
Another interesting that we are thinking about adding towards the end of the class, the sections about interaction with the physical world and interaction with people, is having multiple of them trying to do a collaborative task together. So if we have a block and we bring in like two of them together, how would they work together to move an object if one of them is, let's say, teleoperated and the other one's autonomous? Thinking about challenges there.
Interesting. Fantastic. Anything else you want to add about, does it have a name?
Each one, we have 28 of them.
Oh, and they each have a name.
Yes.
Do you know this one?
So this is Astro.
This is Astro.
But so until last year, they were named after burger recipes. Like there was the Chopper, the Whopper. I didn't know that there were so many different types. But now that we have 28 platforms, we couldn't find the 28 names of burgers. So now we have a different naming scheme.
Okay.